Hello, and welcome to the Concise module for training on Intelligent Transportation Systems Architectures. This training is designed for transportation professionals who want to understand what an ITS architecture is and how a national ITS reference architecture, such as ARC-IT, can be used to support planning and developing integrated transportation systems. Disclaimer: Transport Canada does not endorse products or companies. Reference to any specific commercial products, process, or service by trade name, trademark, manufacturer, or otherwise does not constitute or imply its endorsement, recommendation, or favoring by Transport Canada, and shall not be used for advertising or service endorsement purposes. Transport Canada does not guarantee the accuracy and completeness of information. We would like to acknowledge the assistance and supporting material that has been shared by the U.S. DOT and their ITS architecture contractor. That material contributed considerably to this presentation. We would also like to acknowledge the contributions of the members of the ITS Architecture for Canada Stakeholders Advisory Committee. This module will take a look at the following. First, we are going to start with a look at the role of transportation professionals and an overview of the cycle for planning and project development. Then we will introduce ITS architectures and look at their structure and content. We will then highlight how an ITS architecture may be used and the benefits of doing so. And finally, we will point you to some additional resources of information that may be of interest. What is ITS? To begin, let's first agree on a broad definition of Intelligent Transportation Systems, or ITS. ITS integrates different information and communications technologies into road transportation infrastructure and vehicles to help make the transportation system safer and more efficient. ITS include the electronics, communications, or information processing technologies that may be deployed singly or integrated to implement strategies to address identified needs and objectives from the perspective of a region and/or a specific project. ITS are critical tools in the toolbox of transportation professionals, whose role is to plan and provide solutions to transportation needs. In simplistic terms, transportation professionals identify the transportation needs of a region, which become the basis for the transportation goals and objectives of the region. Transportation professionals then identify solutions to address those goals and objectives. To implement the solutions, transportation professionals first design the necessary facilities and systems and then oversee the development and deployment of those solutions. Once deployed, the systems are then operated and maintained. Let's consider those transportation solutions and the underlying needs, goals, and objectives that they may address. Many factors are considered in the development of regional goals and objectives, including, but not limited to, economic vitality, safety, security, accessibility and mobility options, environmental impact, modal integration and connectivity, and support of efficient management and operation of assets. The goals and objectives may be defined in general terms, such as reduce congestion, or specific terms, such as provide timely road condition information. It is important for a region to have a plan for deploying ITS and technologies to meet those goals and objectives, and ensure that the systems are interoperable and services are consistently provided across the region. That plan can be described in an ITS architecture for that region. As alluded to earlier, transportation professionals are involved in two general areas of transportation: planning and project development. Transportation planning has two key aspects: long-range planning, which looks at providing a framework to achieve transportation goals and objectives and allows a region to coordinate transportation investments over a long horizon, such as 20-plus years. Short-range planning considers programming of projects over a short period, such as 5 years, to achieve compliance with the goals of the long-range transportation plan. Once a project is programmed, a typical process for the development of the project is shown to the right of the vertical line. Project feasibility considers the basic needs of the project and performs any trade-offs or studies regarding how to meet the needs. This may include development of a concept of operations. Environmental considers the environmental impact of the project and obtains any needed approvals before the project can proceed. This step has the sense of defining the requirements that must be satisfied by the project. Preliminary design, sometimes called 30% design, considers basic design elements such as geometric design, structures, pavement, and guidelines for system deployments. Final design, sometimes called plan specification and estimates, PS&E, is the detailed description of what will be constructed. Construction is the actual building and deployment of the project. After construction is complete, the project moves into operations and maintenance phases. This chart starts the discussion of additional planning outputs that are often created to supplement the long-range transportation plan and short-range program plan. When considering ITS projects, those overwhelmingly relate to operations, which doesn't just happen, but does so as the result of operations planning. So let's look at operations planning, which considers problems and solutions, strategies to be implemented, and may be developed around specific problem areas or on a corridor-by-corridor basis. Operations plans look at identifying governing goals and objectives, identification of problems, and then the strategies to address the problems. They also typically address staffing, equipment, and facilities. Because the ITS strategies, such as those relating to capacity management, for example, require devices on the roadway as well as centers that manage the devices, the implementation of ITS is something that needs to be planned for. In addition, many capital transportation projects have technology pieces to them. Think of building a new freeway interchange. It is likely that it will include ITS devices as part of the build. Infrastructure planning that goes beyond the planning done for the roadway is important for the success of an individual project, as well as the overall capital program for an agency. ITS infrastructure planning considers the what, when, and how. With respect to the what, based on the operations plan, it will identify the infrastructure needed to support the operations strategies. This will include the ITS systems, devices, and supporting communications. It will include a logical implementation schedule of projects based on technical considerations for interdependencies of common elements between projects. The final piece of successful planning is an ITS architecture. In most cases, it would be on a regional level and comprehensive, and will provide a framework for an integration plan for all potential capital projects and will integrate and build from information from the operations and infrastructure plans. Later, when an agency has secured funding and approval to proceed with one of the projects, more detailed project ITS architectures can be defined and developed to support both preliminary and detailed design for each individual project. There are a couple of key points here. First, ITS architectures are developed to align with stakeholders' vision for ITS operations and infrastructure planning. And second, between regional and project ITS architectures, they can address both long-term planning strategies and short-term requirements of individual projects. So let's take a quick step back and understand what is an ITS architecture. Basically, it's a reference framework that provides a common basis and language for planning, defining, and integrating ITS into road transportation infrastructure and operations without mandating any particular technology or implementation. The key aspects of an architecture are that it identifies organizations involved, called stakeholders, systems and devices operated, such as centers and vehicles, functions performed by the systems and devices, what information the systems exchange, what communications types are used to exchange the information. A key aspect of an ITS architecture, or other reference framework for that matter, are that they are technology neutral, and they allow for design flexibility for any specific implementation. Let's use the analogy of a buffet. It gives you more than you could ever imagine or need. You can choose to have the beef, chicken, seafood, and/or vegetarian option, and for each you can choose how each are prepared and what ingredients and accompaniments are included. In the rare instance it does not have what you want, it provides the facilities to allow you to prepare it. As mentioned, an ITS architecture provides a reference framework that is technology and design neutral. As such, it should not be interpreted as, nor is it intended to be, a design document. Additionally, It does not define institutional or development processes. One of the fundamental concepts of an ITS architecture is providing a framework for defining integration. This diagram shows the integration of centers as an example and illustrates how end users can benefit from the shared information. This can include travelers directly accessing that information, or traffic management systems using it to manage traffic and advise motorists, and transit and emergency service operators using it to manage their fleets and operations. There are generally three types of ITS architectures. The first, a reference architecture, is a general template covering a wide range of ITS services. An example of this is the Architecture Reference for Cooperative and Intelligent Transportation, ARCIT, provides a national vision for ITS and the concept of how system of systems come together, guides sound ITS planning and investments at government levels, supports systems engineering and analysis for projects deploying ITS, identifies and scopes the needs for standardized interfaces. The second level of architecture is called a regional ITS architecture, which describes the ITS deployed in a specific region, for instance a municipality like York or a province like BC. This level aligns with the ITS architecture discussed earlier as part of the planning phase. The third level of architecture is a project architecture. This can represent a subset of the regional architecture that covers just a single project, for example, implementing a TMC, or it could be developed separately. In either case, a project architecture can be a more detailed view of the stakeholders, systems, and interfaces represented by the project. This level aligns with the ITS architecture discussed earlier as part of the project development phase. For the next few slides, we will concentrate on the highest level, using ARCIT as an example of a reference ITS architecture. A recent jurisdictional scan undertaken for Transport Canada found that the U.S. ARCIT framework is a gold standard for reference ITS architectures, due to its maturity and breadth of coverage as a result of nearly 30 years of history and ongoing enhancement and maintenance. The ITS architecture for Canada has a history of periodically aligning with the U.S., and in the most recent Canadian update, a strategic decision was made to ensure that all common content with ARCIT was directly aligned. The subsequent version 9 of ARCIT integrated the 4 remaining unique Canadian-developed service packages, which had been developed in coordination with the U.S. architecture team. There is now a single common set of databases which the U.S. maintains, and the ARCIT website and supporting tools now fully support the entire ITS architecture for Canada. Given this, the current approach for Transport Canada is to encourage use of ARCIT as opposed to maintaining a parallel architecture, and continue to develop separate and compatible service packages as necessary. ARCIT is a comprehensive framework that supports a wide range of ITS services or service packages. Services are organized within these 12 service areas. In total, there are over 150 service packages which are organized within these 12 service areas. Included in these service packages are a number that are international examples from Europe, Australia, and Canada. The first 2 relate to supporting expedited customs clearance programs and coordination at shared borders. The Signal Enforcement Service Package relates to red light cameras, and the Roadway Micro-Prediction relates to local forecasts needed for focused warning systems. ARCIT has a structure which follows recognized standards for reference architectures and is defined around 4 distinct views. The enterprise view of ARCIT defines relationships between organizations and the roles those organizations play in providing ITS services. The functional view of ARCIT defines the set of processes that implement the functionality required to provide services. The most familiar view of ARCIT is the physical view, which groups the functionality into physical objects and identifies the interfaces between the objects. Finally, the communications view identifies the communication solutions needed to send data along the interfaces defined by the physical view. Let's take a bit of a closer look at each of these views. We'll start with the physical view, as it is the best understood and most used of the 4 views. The physical view represents physical elements that operate in the field and back office, as well as the functionality contained within those elements, the roles those elements play in delivering ITS services, and the connections between those elements. What we are seeing here are the core physical object entities that make up the physical view. They are grouped into common entity categories, including center, field, vehicle, which are basically self-explanatory. There is also a group for personal, which represents devices that the public may use to access ITS services. Finally, a support category which includes systems and devices that align with more traditional IT-type services. Let's consider, from a physical perspective, what may be needed for Transit Signal Priority, TSP. Firstly, you need to have signals equipment in the field, including controllers and signals themselves. There may also be equipment to either detect or communicate with the transit vehicles. You can see that ARC-IT as a reference architecture identifies these as a common ITS roadway equipment object. Next, you have the transit vehicle, and more specifically, the onboard equipment on the vehicle. This may include automatic vehicle location technologies to track the vehicle, communications equipment, and mobile data terminals. Depending on the implementation, you may need central systems at the Transit Management Center to monitor and track schedule performance and evaluate the need for TSP. Similarly, there may need to be central systems at the Traffic Management Center to coordinate with the Transit Management Center or to process requests from the controller in the field. And then there is communications to tie everything together. So the physical view identifies the necessary systems and devices as well as the interfaces between them. Let's now consider the enterprise view, which addresses the policies, funding incentives, working arrangements, and jurisdictional structure that support the technical layers of the architecture. Basically, it is a framework for who is involved in carrying out ITS services and how. Building off the physical view, it is important to identify who is responsible for each entity. For a given city or region, the owners of the Traffic Management Center and ITS roadway equipment would likely be their Transportation Services Division. The owners of the Transit Management Center, transit vehicle, and the onboard equipment would be the city's Transit Service Division or a higher-level regional authority. However, ownership is only one role, and an architecture may identify other stakeholders that may lead different life cycle stages for development, installation, operations, and maintenance. Also, the life cycle of ITS is not so simple. Depending on the stage of a project's life cycle, one or more of these roles may not be known at a particular time. In many cases, particularly in planning future projects, the owner may be identified initially, as they will be responsible for procuring these services. On to the functional view, which provides an analysis of abstract functional elements and their logical interactions, which is basically identifying what is involved in carrying out ITS services. Let's look at just one of the devices we have discussed, the traffic controller in the field. Within ARC-IT, there is a functional entity related to that controller, which is Roadway Field Management Station Operation. Again, you can see that as a reference architecture, the naming is not specific. And under that functional entity are a list of potential functional requirements for that device. These are a menu of shall statements that can be used during planning stages to understand the scoping for a project and or used as a starting point for procurement specifications as the project moves beyond planning. And finally, we have the communications view, which takes the physical interfaces to a lower level of detail, which can be useful for preliminary and detailed design. It provides a framework for identifying the protocols necessary to implement an information flow between the various systems. To the degree possible, ARC-IT provides communication solutions as a reference to all of the interfaces within its framework. Each solution points to relevant standards and protocols. The example here is for the center-to-field interface for signal control commands for NTCIP signal system masters. We won't get into the details, but should highlight that it points to relevant NTCIP and IT standards and provides a wealth of direction to transportation professionals and system designers in particular. So in the preceding slides, we looked at different views of an ITS architecture and illustrated the structure and content of each and used a common example through each view. In essence, we illustrated how ARCIT can be used as a reference framework that can be customized to support an organization's, such as a municipal government's, specific ITS planning and design needs, essentially choosing applicable parts and components and customizing those to fit their plans. So what is considered a traffic management center in ARCIT may be customized more specifically as the municipality's central signal control system, and the ITS roadway equipment more specifically as signals and controllers. At its highest and broadest customization level, that may be to develop a regional ITS architecture to support a suite of projects and initiatives as part of a short or long-range plan. ARCIT includes a software tool called Regional Architecture Development for Intelligent Transportation, or RADIT, which is designed specifically to support regional architecture development. It should also be noted that RADIT is an updated and rebranded version of the previous Turbo software tool. Taking it one step further, the most detailed level of customization would be to develop a project ITS architecture focused on a specific ITS deployment project. Again, ARCIT provides a systems engineering tool for intelligent transportation, or SETIT tool, to develop and define these detailed elements. With respect to using ARCIT to develop lower-level architectures, it is important to emphasize a couple of things. 1. ARCIT is a very mature reference architecture whose origin dates back to the early 90s and is the product of significant amount of stakeholder effort and investment made to continue its evolution, expansion, and maintenance. 2. In the U.S., they mandate that all projects that include federal funding are required to follow a systems engineering process and be included in an architecture. This is not related to highest reference level of architecture, but means that the project must be included in either regional planning architectures or one specific to the project. 3. These mandates are not in place at the whim of the FHWA and USDOT. They are there based on their assessments of best practices. As a result, there are hundreds of regional architectures in the U.S. with essentially all metropolitan planning organizations, or MPOs, each having one that supports their planning efforts, which may help with access to federal funds. 4. Canada does not have similar requirements, and as a result, there has not been the same uptake and use of the architecture here as in the U.S. That said, using an ITS architecture is a good practice, and there are many benefits to doing so. Now consider the previously discussed project planning and development lifecycle, and how ITS architecture application can be integrated into the process. Let's consider it as more of a cyclical process, as illustrated on the right. Efficient transportation planning is not just related to new projects and initiatives, but also needs to consider existing legacy ITS systems and operations, and evaluating when there will be needs for updates and enhancements and, when necessary, replacement. We have discussed how application of the ARCIT reference architecture can be useful during an agency's transportation planning efforts to ensure that their long-range plans align with the needs and vision, and that their short-range plans incorporate programming and budgeting of projects in a logical and achievable sequence. Development of a regional architecture using the RADIT tool may be a key supporting task to achieve these goals. It can help identify opportunities for additional information sharing and to promote integration of planned projects. Based on the short-range plan for capital projects, further development of ITS project architectures can also help support the design and procurement of those. By defining projects in greater detail, programming or budgeting processes are also easier. So let's look at some of the reasons for or benefits of developing customized region and project-specific ITS architectures. First, regional architectures are developed to support capital plans which are themselves developed based on regional needs and vision. Integrating architecture development into the planning process can ensure continuity to those needs and that vision are maintained. Integration into the planning process, particularly early on, can also help reduce risks overall and improve chances of success for each of the planned ITS projects and initiatives. ARCIT is a mature and comprehensive reference architecture and provides a common set of industry-standard vocabulary and nomenclature, which can bring consistent language to stakeholder planning efforts and engagements, as well as consistent content and structure to documenting projects. ARCIT can also help identify additional possibilities with respect to system functionality and broader information sharing. Additionally, the RADit and SETit software suite are built to ensure that common physical systems and devices are consistent across multiple projects and initiatives. And finally, ensuring compliance with the relevant and recent standards can make it much cheaper to procure and integrate faulty or outdated equipment. It is important to note that stakeholder involvement and input is critical to the success of ITS projects and operations. This includes ensuring that all stakeholders are engaged, not just the planners, but also those that will be involved in operations. In many cases, the development of a regional ITS architecture can be a catalyst that brings together planning and operations professionals in a region. Initial architecture development puts planners and operators on the same page, and periodic coordinated updates keep them on the same page. There have been examples where using the same committee that supported architecture development to also provide oversight over architecture use and maintenance has proven successful by building on the architecture development experience and the established relationships to keep ITS and broader operations initiatives coordinated and moving forward. If you are interested in more information, the majority of resources available to you can be found either from Transport Canada or the ARCIT website. The Transport Canada website address is shown here and is dedicated to ITS architectures. You will be able to access documents and guides that have been produced by or for Transport Canada. It will also have the latest information on any planned training programs or offerings. There is also dedicated support email that you can send inquiries to. The ARCIT website is where all of the ARCIT content is hosted and available in an easy-to-navigate hypertext format. In addition, it also includes access to a wealth of other resources, including a series of recorded training sessions that will allow you to stream at your convenience. The recordings relate to ARCIT and its use, as well as how to use RADit and SETit tools. Other content includes access to the RADit and SETit tools themselves, and relevant primers, guides, and handbooks. This module introduced ITS architectures and an overview of how the ARCIT reference architecture can be used to support planning and project development. Now you hopefully understand that ITS architectures provide a framework for developing integrated transportation systems. ARCIT itself is a reference architecture that is comprised of 4 complementary views, and together with the RADit and SETit tools provides resources that can help support transportation professionals with planning and project design for ITS deployments and operations. Such application of ARCIT can be integrated into day-to-day planning and programming processes.